going. So this is a slide deck from one of my colleagues, Alwyn Antrick, who's pretty big in the Proxmox space and is our head of training and head of Proxmox at Croit. And he just gave this talk at Prox Talks just a few weeks ago. So RAM is the new gold, and I think we're all pretty aware of the big issues that we're having right now with RAM. And so today we're going to be covering practical strategies and software side settings that we can do in Proxmox to stretch your physical RAM further. Everything that we're going to talk about today is built into Proxmox or the Linux kernel, so no exotic patches or unsupported hacks or anything like that. Everything's going to be accessible, mostly accessible through the GUI. Quick background on Croit. Evan just discussed what we do, but overall you can kind of see here, we've got customers around the world, we've got global staff, and we have a Croit Ceph software manager that goes and deploys Ceph environments. In addition to that, we do Proxmox. So we have support in those areas, consulting, and training as well. And then it made a boom, a big AI boom. And the RAM prices followed. So we all know that AI needs massive amounts of memory. The bigger issue is kind of indirect. AI uses a special type of memory called high bandwidth memory. And that process to create that actually takes about 3 or 4 times the amount of effort per gigabyte as compared to standard DDR5. So a lot of manufacturing shifted towards that because it's more profitable. That has starved the DDR5 supply chain. And on top of that, a lot of servers that are running big AI rigs, they still also need that DDR5 as well. Industry analysts don't really see relief for this until about 2027. So the question is what can we do with the RAM that we have already? And here's a chart of gold versus DDR5. And as you can see, it's pretty wild. I wish that I had a stockpile of DDR right about then, but you can see that there was a brief dip, but that was probably because of the Chinese New Year's. But overall, the trend is clear. That thing is going up. And so I'm sure plenty of RAM was used in the making of this chart, but this is the topics that we're going to be going through today. So we're going to be talking about ZRAM and ZSwap for compressed swap, KSM for memory deduplication, memory ballooning for dynamic allocation across the VMs themselves, ZFS arc tuning for storage overhead, and then containers versus VMs as an architecture choice. So ZRAM and ZSwap. Before we get too far, let's talk about swap on a hypervisor. Fair warning, this topic sparks strong opinions if you're familiar with what swap is, but if you're not, a quick background is swap is disk space on the OS, or that the OS uses as an overflow when physical RAM runs out. If you're used to Windows, it's called a page file. It's a big file that you see that eats up a whole ton of your hard drive space. You can think of swap like an overflow parking lot. It's further and slower from the venue that you're trying to get to, but it gives you a place to park when the main lot is full. So the question is, for a hypervisor, do you even want swap? And if so, where should it live? So this is an LS block output showing the default swap for Proxmox install. And if you notice the highlighted red line, the PVE swap is about 4 gigs sitting on an LVM volume on the same disk that the OS is living on. That's the default for ext4 and XFS installations. Quick note, ZFS doesn't create swap at all on Proxmox if you install the operating system with ZFS. For a regular server, this is fine, but on a hypervisor, every VM is a process whose memory kernel manages. When heavy swapping starts on the OS disk, it competes for I/O with every single thing that is running on that disk, including the OS itself. The memory management also, if you're running Ceph, the Ceph metadata that you're running, if you're running a hyper-converged environment, and really what happens in practice is the system becomes unresponsive, you can't SSH in, and you end up having to hard reset the machine. So you better hope that you have IPMI configured correctly. For anyone running Ceph hyperconverged, Proxmox puts the Ceph mon databases on the OS disk. If swap saturates that disk, your Ceph monitors starve, and you now have a storage cluster problem on top of a host problem. So option A, disable swap entirely. That's what some people do. If you have a proper HA and redundancy configured in with the Proxmox cluster, you just let the host die and fail over. Go about your business. Option B, move swap to a dedicated hopefully fast NVMe, so that swap I/O can't starve the OS when you get into those situations. Either way, avoiding leaving the defaults is going to be best. So you want to tune one or the other. The VM swappiness. So here is a table kind of showing what is common. It controls how aggressive Linux moves the memory pages to swap. A few key values is 60 is the kernel default. This is usually too aggressive for a hypervisor. 10 is a commonly recommended value for Proxmox. This prefers RAM and only swaps when things get tight. An important correction for anybody reading older Proxmox documentation, swap 0 doesn't mean only swap to avoid out of memory. On modern kernels, anything past 3.5, setting to 0 is extremely aggressive. The kernel won't swap until free memory drops below a certain watermark, and paradoxically, that can trigger to kill even the swap space when it's available. If you want the old swap only when truly needed behavior, use swappiness of 1 instead. It's also worth noting that since the kernel 5.8, the valid range has been extended from 0 to 100 up to 200. And values above 100 tell the kernel that the swap I/O is actually cheaper than file system I/O. This is relevant if you're using ZRAM, which we're going to be talking about here shortly, since compressed in-memory swap is faster than the disk itself. Some Linux distributions use a value of 180 by default. So overall, setting swappiness to 10 is still generally the recommendation and considered safe. But you need to make sure that you do create the swappiness config file and get that configured. So let's talk about two smarter approaches to swap. ZRAM creates a block device entirely in RAM that acts as compressed swap. You can think of it as a zip file for your overflow memory. Instead of writing a slow disk, ZRAM compresses pages and keeps them in RAM. And you typically get a 2-to-1 or much higher compression for that. The trade-off is CPU cycles. You can't get anything for free. But compared to disk I/O latency, that's a pretty big win. So ZSwap takes a different approach. It's a compressed cache that sits in front of your regular swap disk. When a page would go to disk, ZSwap intercepts it, compresses it, and holds it in a RAM pool. Only when the pool fills does data hit the disk. So it's kind of like a middle tier for that. The key difference, ZRAM replaces the disk swap. ZSwap supplements it. But a critical point is do not combine ZRAM and ZSwap because ZSwap intercepts pages before they even ever reach any swap device, including ZRAM itself. So if both are active, ZSwap grabs everything first, and ZRAM just sits idle, wasting memory that you allocated to it. So pick one or the other. And here is a real system, so that has some screenshots, running ZRAM. The ZRAM control output shows here 410 megabytes of compressed down to 78 megabytes compressed. So that's a 5-to-1 ratio. That's excellent, and it's not unrealistic for workloads with idle processes or repetitive data. Configuration is straightforward via the ZRAM swap package. You set the algorithm, the compression algorithm. The size, you can set the size as a percentage of the RAM, and a priority, so ZRAM is preferred over disk swap itself. One thing to note is the config file here shows algorithm as ZL4, but if you look at the ZRAM output, it shows Z standard. So this is a common gotcha. There's multiple configurations that can override each other. The config file, UDEV rules, kernel defaults, so make sure you always verify what's actually running with ZRAM control, not just what the first config file that you look at says. Below that, you see the ZSwap debug stats from sysfs. This is just shown as reference. Remember, you use one or the other, not both. In a real-world anecdote that we had from our support team, we deployed ZRAM for a customer running Ceph who couldn't fit all of their OSD recovery processes in memory simultaneously. ZRAM's compression freed up just enough RAM to keep everything running and complete the recovery. Without it, they would have needed more RAM ASAP at premium pricing. Next topic is kernel same page merging, and you can think of this basically as this is memory deduplication. This is built into Proxmox and enabled by default. And this is basically a diagram showing a before and after of KSM. On the left, that's without KSM. You can see all physical pages are being used. And on the right, with KSM, the identical pages are merged into a shared page. The shared pages are marked copy on write, so if any VM modifies a shared page, the kernel gives it its own private copy. VMs don't know that this is happening. The savings are greatest when running many similar VMs, so think same OS, same application type, same versioning. VDI environments are kind of the classic example where you're just getting a lot of the same. And this is the KSM stats that you see in the Proxmox GUI. If you notice the KSM sharing metric, that's about 24.87 gigabytes of shared memory on this system. That's real RAM that's reclaimed. This is visible right in the UI. No command line is needed for this. And for capacity planners, this metric directly tells you how much the RAM deduplication is actually saving you. So obviously, if it's a lot, you can decide what types of things are running, hopefully on the same type of host within the same cluster to try to maximize that benefit. This is an output of the KSM sysfs parameters. For engineers that want to tune this, the pages to scan controls how many KSM pages there are that KSM examines per cycle. The sleep milliseconds controls the interval between these cycles. Page sharing is your savings metric. There's also an advisor mode that can auto-tune these rates by scanning and basing things on a CPU budget target. There is something to bring up though, a security consideration on this. KSM has been demonstrated vulnerable to side channel attacks in academic research. This is acknowledged in the Proxmox wiki. Basically by timing memory access patterns, one VM can potentially infer what software is running on another VM. So basically in a multi-tenant environment, you could choose to disable KSM if you're trying to be ultra secure in that environment. You can also disable it per VM, and there is an example given for that. So if you're running multiple customers all in the same environment, one maybe has that additional concern, you can just turn it off for their VMs instead of the whole environment, and you're still getting the benefits elsewhere. The next section is going to be dynamic memory ballooning. So the hypervisor dynamically reclaims unused memory from idle VMs and makes it available to busy ones. And here is how it works. Say VM1 has a light workload and has allocated 8 gigs, but is only actually using 3 gigs. And VM2 needs more memory. The balloon driver runs inside the guest as a VirtIO device. It inflates inside of VM1 and allocates memory so that the guest itself can't use it. The hypervisor marks that memory as free on the host so that it can give it to VM2. When VM1 needs the memory back, the balloon deflates, and this terminology is counterintuitive. Inflate actually means that the VM loses usable RAM. You can kind of think of it as a balloon, as a space occupier inside the VM, and I like to think of it as a bouncy house inflating inside of the living room. Another important consideration, the VirtIO balloon driver must be installed in the guest. So with Linux, this usually works well out of the box because VirtIO drivers are usually included. For Windows guests, you do need to make sure that you install the VirtIO drivers separately, but realistically, you should be installing the VirtIO drivers anyway. So now we're going to talk. This is a screenshot of how to actually configure this in Proxmox. So you set a maximum memory and a minimum memory there for the VM in question. The balloon adjusts dynamically between those two values based on the actual usage. And a pro tip is, even if you're not using ballooning for reclamation, keep the balloon device enabled, because without it, the hypervisor has no visibility into the guest's actual memory usage. So with it on, you get accurate used versus allocated metrics in the UI. Now talking about ZFS, something that is technically a storage topic, but has potentially a massive impact on the available RAM of the Proxmox system. If you're not familiar with ZFS, it's a combined file system and volume manager that's very Proxmox and Linux in general, but especially with Proxmox. It's excellent, but it can be RAM hungry. So, ZFS ARC. Actually, it doesn't say, oh yeah, ZFS ARC. So if you look on that graphic, what that is the adaptive replacement cache, or ARC, is an in-memory read cache. So how much RAM does it take by default? The short answer is it depends on whether the Proxmox installer set a limit for you. If you install Proxmox 8.1 or later on a ZFS root disk, the installer automatically caps the ARC at about 10% of RAM, up to 16 gigabytes. And that's quite conservative, so you'd probably be fine. But if you added ZFS after the installation, or if you're running an older version, no installer limit exists, and the upstream OpenZFS defaults apply. That used to be 50% of RAM, and with OpenZFS 2.3, which is included in Proxmox 9, it's even higher. The bottom line is, check what your system is actually set to, run ARC summary, or look at the ZFS.com. A rule of thumb for sizing is the current Proxmox documentation recommends 2 gigabytes base plus 1 gigabyte per terabyte of storage as a guideline for ARC. Anything above that is nice for read caching. And you can cap the ZFS ARC with the ZFS ARC max parameter. So if you want something lower, you can have something lower. Again, this is just in-memory cache for very fast writes. So for admins, if your ZFS host seems to have less RAM available than you would expect, this is a great place to check. And then we're going to talk about ZFS compression. ZFS supports transparent compression, and enabling it is essentially free performance if you are using ZFS. So with LZ4 compression, your effective storage capacity increases. And counterintuitively, performance also improves because there's less data to physically read and write from the disk. LZ4 runs at over 500 megabytes per core, with decompression being even faster. That far exceeds typical disk throughput, which is why, again, kind of counterintuitive, but the performance usually goes up. You're just trading some CPU cycles to read essentially less actual bits of data off of the disk. ZFS also has a smart early abort feature. So if the first pass shows that data won't compress well, it skips the compression entirely. This doesn't directly save RAM, but it reduces I/O pressure on the storage, which helps the whole system. And if we are talking about swap sitting on a disk, then having less overall I/O on that particular disk is going to be a good thing because it potentially allows additional time, CPU for, again, helping with that compression and improving overall performance on that disk. And then here is where in the GUI you would configure that. So LZ4 is a safe default, but Z standard offers better compression ratios at slightly higher CPU cost. Today's modern CPUs, they're so fast that you probably won't even see too much of a difference between the two. But this is a checkbox level decision most environments should enable. This only works where compression hertz are data that's already compressed. Basically, if the files are already compressed, like video files, media files, or it's a compressed backup, then you're probably not going to see too much of a benefit for this. Now talking about containers or VMs. So this is a strategic decision, and on the left here, we have KVM virtual machines. Each VM runs a full operating system with its own kernel, its own memory space, complete hardware emulation. The pro is it has strong isolation, but some significant overhead from an OS standpoint. Every VM needs its own kernel and system services just to exist. On the right, we've got LXC containers. Containers share the host Linux kernel, no hardware emulation. You can think of VMs as separate houses, each with their own plumbing and electrical. Containers are more like apartments, separate living spaces sharing the same building's infrastructure. The memory difference is significant between VMs and containers. A minimum container might use 16 to 128 megs of memory. A comparable VM might be 512 or a gig, or much more, before you even actually layer the workload of what it's actually doing on top of that. The biggest trade-off is typically isolation. VMs provide stronger security boundaries. Containers share the kernel, so a kernel vulnerability could potentially affect all containers. Some practical impact. If you convert 20 lightweight Linux VMs to containers, you might free up 10 to 20 gigs of RAM just on overhead alone. And at current prices, that's a pretty big deal. Also, this isn't an all or nothing. Many Proxmox environments use both. VMs for workloads needing strong isolation, or just because that's how it's needed. And if you can run containers for everything else, then run containers for everything else. And I'll go over this quick bonus. So if you do use ZRAM and are in a memory pinch, there's a nice trick that you can do with ZRAM. It allows you to offload to a physical backing device. So again, remember, ZRAM is essentially just a block device that is sitting in physical memory, and you're allowed to compress that because it's treating it as a block device. Well, what you can do is offload certain types of pages then from that ZRAM block device to an actual physical disk. Ideally, something fast like an NVMe. You can kind of think of this as a tiered system. Your best data stays compressed in RAM, but pages that don't compress well or have been idle can move out to that disk to free up that RAM for pages that actually benefit it being there. There are several write-back triggers, like huge, targets pages that are compressed poorly, and idle, which targets cold pages, so things that haven't been accessed within a certain time frame. You're able to define that time frame. Huge idle, that combines both. And incompressible, which specifies target pages that no algorithm could compress at all. The configuration is straightforward. You point ZRAM at an unformatted partition, and you set your write-back mode. And for idle pages, set the idle threshold in seconds, so like an hour or so, or 3,600, about an hour works well. One caveat is that ZRAM does not automatically write pages to the backing device on an ongoing basis. So the initial write-back mode gets set, but for idle pages, write-backs, for them to happen continuously, you need a systemd timer or a cron job that periodically marks pages as idle and triggers the write-back. So something like a script that runs every hour. There's a UDEV rule shown at the bottom that wraps the initial setup into a single command that runs at boot. The backing partition doesn't need a file system, but you do need to make sure that that partition has been zeroed out beforehand. So this is a nice complement to the ZRAM setup we discussed earlier, because basically you get the speed of compressed RAM for your hot data and a fast NVMe safety net for anything else. Now, note, you're still swapping. Ideally, you don't want to ever be swapping, if possible. So this isn't looked at as like a long-term solution. And you do, hopefully, at a later time, when you've gotten your RAM situation more under control, if this is just being used in an emergency, you need to get those pages back in memory and hopefully out of the physical disk swap. All right, so to wrap up, we went over some practical strategies for optimizing RAM and Proxmox. So tuning or reallocating swap. Don't let it sit on your OS disk. Set the swappiness to 10 is the generally accepted safe default. But if you are doing things like ZRAM, you can crank that up to something over 100. Enable KSM if you run very similar VMs. Use ballooning at a minimum for metrics, but ideally for the allocation aspect of it. Then also check your ZFS ARC to make sure that you're not having too big of a ZFS cache that's just sitting there chewing up your memory. And then finally, consider containers where VM isolation isn't required, and you can really get a big benefit out of the reduction in memory that a VM would take compared to a container.